Welcome back to the session after lunch. I'm sure that this presentation will keep you awake despite having lunch. Olege Petrovsky's been in security for well over 20 years. He's a malware researcher. He likes to explore the Internet of Things, and when he's not hijacking drones, he's scaring cats and dogs with drones.
Absolutely. Thank you, Randy. Good afternoon, everyone. As Randy said, my name is Olege Petrovsky, and I'm a part of the HP malware research team. For the next half hour, I will be talking about drones, the underlying technology, and security issues which might accompany certain drones configurations. I personally started building multi-rotors about 5 years ago, and since then it has become a passion of mine. I don't like using the word drones per se, and favor more descriptive names such as remote control, model, multi-rotor, an unmanned aerial vehicle, or an unmanned aerial system. But mass media seems to like it and use it in a multitude of scenarios, and hence making the public very well aware of it. So during the presentation, you hear me using all those terminologies interchangeably. So I don't know how everyone feels, but I think we are witnessing a quiet revolution. And it is not just self-driven electric cars, cheap space flights, smart TVs, smart blenders, homes, and robotic vacuum cleaners. Drones. Drones, which are often heard of as ominous, unseen destroyers of peace and privacy, the creators of conundrums for lawmakers and politicians. Do we love them? Do we fear them? As a matter of fact, I happen to have one here. So I'm going to position it right here. So I don't know what if it looks ominous to you, but hopefully it does. And yes, it did not fly on its own over Atlantic. I wish it could. And it's not self-aware yet, but we'll see. So even those close to the subject cannot agree what a drone is and whether we should call them drones at all. But there's one thing certain: this industry is booming. According to aerospace research firm Thiel Group, within the next decade, the commercial applications for unmanned aerial vehicles could fuel an economic boom in excess of $11 billion. During this presentation, I hope to look at various popular multi-rotor unmanned aerial vehicle systems and analyze them for susceptibility to known and proof-of-concept security attacks. The idea is to look at the underlying technology and highlight possible weaknesses from the malware security point of view. So, how popular the topics concerning drones are anyway? Let's quickly look at the prevalence of the drone search against malware. It looks like, despite the importance of the global security issue somewhere around the beginning of 2014, here, malware topic started to give way to drones. Well, you might say malware, maybe that is not as important as the topic. Let's compare it to global warming. And don't get me wrong, this is a very serious issue. I say, looking at this data, I think we should use drones to combat global warming while hopefully keeping malware away. And in the end, it should magically somehow work itself out. Even though multi-rotor UAVs might range from nano-sized to ones capable of lifting a human-sized payload and look very different, the majority of them follow the same principal design. It consists of the flight controller, which is connected to the radio receiver, the electronic speed controller, abbreviated as ESC, and the power distribution board. The AC units are in turn connected to electric motors and distribute power to them from a high discharge rate and density lithium polymer battery. The GPS unit and the optional telemetry and command link radio are connected to the flight controller over a serial interface, USR to SPI. The flight control is one of the most important blocks which, pardon the pun, does the heavy lifting of in-flight control and stabilization. It normally consists of an 8 or 32-bit embedded microcontroller system on a chip and is connected to an onboard block of sensors for gauging its spatial orientation. The entire system is controlled via a feedback loop, parameters of which include sensor modules, GPS, the radio receiver, and the telemetry data link inputs. The control loop conforms to a proportional integral derivative mechanism, also known as the PID method. And the PID itself is a method of automation, is often found in industrial control systems, and is aimed at reducing the error between measured and the set point values. The IC translates the pulse width modulation control signals issued by the flight controller into the speed with which the thrust motors turn, affecting the position of the multi-rotor in space, so hence establishing the feedback loop. The block of sensors consists of a variety of inertial measurement units, also known as IMU, which are responsible for the 6th degree of freedom, aerial vehicle and spatial orientation. The IMU sensors group usually include two 3D-dimensional electrical mechanical systems, an accelerometer and a gyroscope. One IMU group is housed in the same chip. So when the IMU group is housed in the same chip, it reduces electrical noise and resistance sensitivity. That's why we often see that the 3D sensors are combined and normally distributed as one IC. The sensor group can also include a magnetic orientation sensor, a barometric pressure sensor, and a GPS unit. All of these sensors contribute another 5 degrees of freedom. So in total, then, an average multi-rotor relies on up to 11 degrees of freedom in spatial orientation and for the feedback loop. The sensors communicate with the embedded CPU of a flight controller using low bandwidth serial protocols such as I2C, SPI, or UART. The convenience of daisy chaining the sensors and using only 2 lines of communication highlights the I2C protocol as one of the preferable choices. I quickly want to go through the popular flight controllers so we understand what we're dealing with here. There is a range of the popular flight controllers which are preferred among the do-it-yourself makers community, some of which made their way to a semi-professional range of multi-rotors. The list is by no means complete, but the market being as it is, one could reasonably expect potential malware writers to be keenly aware of these commonly used systems. The evolution of multi-rotor controllers began approximately 9 years ago. Initially, they rely on an 8-bit CPUs, limited amount of flash memory, and basic sensor blocks. Those basic sensor blocks often consisted of piezoelectric gyro sensors. And if you look here at the picture, those are the piezoelectric gyro sensors, which are like extremely outdated technology. It continued to evolve, including more powerful 8-bit processors and advanced sensor technology, which proved to be more accurate and less prone to electrical interference. It often started to include magnetic, barometric, and GPS sensors. So, as in here on this picture, you see this is the barometric sensor that gauges the height, and the magnetic sensor here, and all the in spatial orientation sensors, including gyroscope and accelerometers, are housed in this chip altogether, which I mentioned earlier reduces interference and makes it more accurate. With the hardware, there were vast improvements in the firmware, often contributed to and tested by a large community of enthusiasts and academia. In many cases, it quickly grew and matured into elaborate and future-rich platforms. The ever-increased demand for complex flight controller features and stability of flight required more and more powerful hardware platforms. The controllers often began to rely on 32-bit processors, which could handle more sophisticated firmware in real time. Some units have multiple processors, which in case of in-flight fail scenarios provide redundancy of critical components. This is just like in commercial aviation systems. And hence, this technology contributes to a safe emergency landing should something terrible happen. Large communal effort goes into research and development of software, firmware, and hardware of flight controllers. The field is rapidly growing. There is often a competition even amongst open source and hardware groups, which results in many variations of firmware code and its portability to a variety of hardware platforms. Comparing these popular flight controllers through Google Trends, with some degree of certainty, we could conclude that ArduCopter and Pixhawks are leading flight controllers, closely followed by multi-V. So if I wanted to mount an attack, I might concentrate on those hardware platforms. Also, as I mentioned earlier, the flight controllers are quite similar in an overall design and most likely be susceptible to a similar kind of malicious attacks. A flight controller of a medium to high complexity is most likely to be set up and controlled through a dedicated piece of software, also known as a ground control station. The ground control station runs on a PC or a mobile platform such as a phone or a tablet and communicates to a flight controller by means of a specialized protocol, either wirelessly or through a USB cable, if a multi-rotor is stationary. So allow me to demonstrate. So currently we have, what do we see? Unfortunately, we cannot fit on the screen entirely, but currently we have the multi-rotor connected to the link, and you can see wirelessly responds to special orientations, and as well as allows to read many points of control over features of the UAV, and many parameters can be changed which are responsible for a safe flight or pre-programmed mission. For instance, here, hopefully it can be seen. And by the way, this is not where we are because the GPS is not engaged. As you can see, GPS no fix under this roof. But what we can do to demonstrate, I want to write down to the flight controller the home location, of expected home location of the device. So I selected the home location here, somewhere in the town of Jenikov. Sorry if I'm reading it wrong. And I'm going to write it into the flight controller. Now to check that we successfully wrote it there, so we read it again, and yeah, the home location is there. And again, all of the parameters which are controlled for the flight and set up and configuration here, everything is communicated through the serial link to the drone and can be read and written to. Quickly coming back. So a ground control station interface, which we just looked at, includes many points of control over features of UAV. Many parameters can be changed, which are responsible for a safe flight or a pre-programmed mission. The software communicates to a flight controller over a serial link using command and control protocol. There are a number of protocols designed to handle communication of a flight controller with a ground control station. Such protocols are used to provide various telemetry and parameter information to and from the ground control station. They are designed to be lightweight and efficient in marshalling high-level language type structures over a serial link. The communication handled by these protocols is fast and in most cases is not secure. The security is expected to be handled by the wireless transport protocols operating in a sub-gigahertz, which could be industrial, scientific, and medical ISM band, or within Wi-Fi radio frequencies, which is, as we know, 2.4 or 5 at this stage, gigahertz. Here's an example of one of such protocol message. So as you can see, even though there is a CRC, which is calculated on the entire, excluding excluding the header bits of information here. The CRC algorithm is well known. The variable payload is not encrypted. Pretty much everything is not, it's plain. So you can easily amend and reconstruct, rebuild the packet if you need to. In many cases, firmware can be modified and uploaded to flight control to alter its behavior. There are a number of areas in which modified firmware can be made to act maliciously. Firmware updates in majority of cases are relying on bootloaders and are not authenticated. In many cases, the bootloaders can be triggered through software mechanism without user confirmation or interaction. And even if user interaction is necessary, because of lack of authentication mechanism, malware can still alter the firmware during the upload process through a serial link injection and filtering. The communication layer from the ground control station to flight controller would look something like this. So we have a flight controller here, the USB to COM driver bridge, and the actual ground control station communicating through the COM port, through the bridge, back and forward to a flight controller. Normally, once the port is opened by ground control station, it cannot be accessed by another application at the user level privilege. But there is a window of opportunity to mount an attack between when the port becomes available and is connected to the ground control station. So you can see on the slide, once we plug in the flight controller to the computer, there is a window of opportunity in which the third-party application can connect to the COM port and do everything that it needs to be doing. And that could be malicious. So, and it could be malicious again. So allow me a little demonstration here. So again, we're going back to a flight control, ground control station. And disconnect. Also, remember where we had our home position, which I'm going to show you again. Here. So I'm going to load the home position that we had before. So, as you remember, it was in this city, Janikov. So I'm going to start up the program that I wrote, connect to the flight controller over a COM port. Immediately we can see the packets that are going back and forward right there. And I'm going to change the home position, basically sending this special command. And now if we're gonna go back to the flight control station, connect. Just make sure that I disconnected there. As I mentioned, we cannot, if the COM port is occupied, I will not be able to connect. So yeah, I disconnected. It's gonna connect again using the ground control station. So currently what's happening, it acquires all the parameters that are stored in the non-volatile memory of the flight controller. So it is aware of all of the preferences. And now if I, again, remember where it was, and now if I read, you'll see that it used to be here, and I altered it to here. Basically, if we're not going to check, that's what could be happening. There's no authentication, or there is no mechanism to prevent this from happening. A more sophisticated attack can be carried out when relying on a filtered driver. The third-party software can intercept and inject the packets into the COM serial communication stream between the ground control station and the USB to SAT bridge driver. So you can see we can have a filtered driver, an application, and application can be malicious. To escape the burden of writing and debugging the filter driver for the purpose of this paper, I used COM0 driver, which is available as an open source. What this driver does, it essentially creates and links to each other any number of pairs of virtual COM ports. Having a pair of COM ports allowed me to recreate the following scenario, which closely resembles an attack performed with the use of the filter driver. The link is established through the USB to USR bridge and then passed through an application before proceeding to a ground control station. The application has total control over the command link and update stream. As a demonstration, I will attempt to intercept and alter traffic to and from the ground control station and the flight controller. So again, first I'm going to disconnect. I'm going to connect quickly here. I'm going to create the scenario I described previously. I'm going to be reading from and sending from COM4 and passing it to COM6. So pretty much man-in-the-middle attack, positioning myself in between the lines of communication. So now, if I connect using ground control station to COM5, all the traffic will be passing through my application, and I'll be able to see it and alter it at will. So again, the parameters are read from the flight controller. Let's load a waypoint file I prepared earlier. And as I can see, it's a nice circle. Now I'm going to try to write this into the flight controller. So this is a mission plan. So starting from home location, it goes to waypoint 1 and so forth around until it finishes, finishes at around 7 and lands at home position. So I'm going to write these waypoints. And as a test, I want to read them again. And voila. I was writing 1, and I'm reading another. What just happened? The application in the middle intercepted the traffic right here and altered. That's all the traffic that had been intercepted and altered in the process of communication. As I mentioned earlier, the serial link can be wrapped into the transport layer, such as Wi-Fi, Bluetooth, or ISM band radio. As an example of the transport link implementation, the 3D radio, which I'm using currently here, now employing a variety of spread spectrum technologies such as frequency hopping and time division multiplexing. The channel sequencing is based on net ID. Within the channel, the radio uses Gaussian frequency shift keying modulation. And here, you can see the waterfall spectrum captured by the software-defined radio. Also can be seen that the golden key sequence is repetitive and can be reverse engineered. The time is represented by a vertical axis and increases downwards. Each white line represents a block of communication happening within a defined time slice and frequency. Within the block, the protocol is using JFSK, as I mentioned earlier, for the digital signal transmission to and from the flight controller and the ground control station. There are other vectors of attack which are more complex in its implementation, such as, for instance, GPS spoofing and sensor firmware modification. These are unlikely to be carried out provided there are simpler and more effective methods of attacks available. Well, in the conclusion, I'd like to say that, first of all, we're experiencing a shift towards more powerful hardware platforms in embedded designs, and UAVs are no exception. With the increasing availability of embedded devices and their presence in various areas of our life comes a responsibility to harden and secure these platforms from malicious attacks and rogue software. Special consideration has to be given to securing firmware on embedded UAV modules. Best practices have to be followed in securing such platforms. Oh, sorry. And following security firmware starting from its architectural design, implementation, and software development processes. The use of secure bootloaders and mechanism of firmware authentication and encryption has to become ubiquitous. Attention has to be given to the use of encryption for wireless control and telemetry protocols. I hope this presentation will help to better understand the UAV technology and will promote a healthy discussion on how to make it more secure without hopefully pointing fingers and blaming anyone. Especially the developing and scientific community, which worked and continues to work exceptionally hard to make this technology available to masses. Also, as a final, we have time, we have a bit more time, no? 2 minutes? Following Chekhov's famous Russian writer dramatic principle, which loosely narrates as follows: if in the first act of a play you have hung a pistol on the wall, then in the following one it should be fired. Otherwise, don't put it there. I'm referring to this quad on the table, and let me show you why we are not flying if it's there in the audience today, and why it would be a bad idea to do so. So as a little piece of demonstration, I'm going to show you here. Just make sure. Disconnect. So what I'm going to do is to hopefully prepare it earlier. I'm going to take a couple of pieces of paper here, probably about 5 or 4 of them. So now it's like half the throttle it's supposed to be for flying. And so this can happen to face or whatever. So, you know. And that is why it's a bad idea to make it insecure. All right. This is
Time, I'm sorry.
This is it. Yeah.
Well, want to thank Oleg for his presentation. There's not time for questions, but if you come down to the bar later on, he's going to be flying around stealing your drink.
Absolutely. Thank you, Randy.
Thank you very much.
Thank you very much.